Session 3 and 4 taught by Dr. Reams in Black in 1977. This is tape 27 side A.
Friday, 10:20 a.m., July the 1st, 1977, Dr. Reams Biological Theory of Ionization, class number 3 and 4, held at Murrieta Hot Springs, California Resort, Murrieta, California. Jack Pfeiffer dwells on logarithms. Bob Pike dwells on definition. Tape number 27-6/27-7/1-77.
Oh, what was the answer? Let's see. We got the 5 and 5 and 5 is 15 minus the 4 and minus the 2, which was 2 to the 9th. Is that correct? And the answer is 512. Okay. Okay. All right. No. Okay. Okay. 32 is 2 to the 5th. So we got a 5 and a 5 and a 5. It's 15. We're in division. Here's a 4 because 2 to the 4 is 16. There's a 2. Okay, you could add these two together. Why? Because this is 16 times 4 down here. Okay? So that would be 6. This is 15 minus 6, giving us 9. 9 is the log of the answer. Now you see why you can quickly do calculations in your head if you simply memorize the log table. Okay. I didn't say the log table was simple. All right. Can we proceed to some powers and roots now? Just one or two? Okay. This is slightly different. We don't want to bore you with the same thing over and over. Question? One more of the combination? Okay. I have not memorized that base 2 table, so it's kind of hard to keep up. I'll have to ask for the answer. All right, let's, because we've got to get to base 1 for the relative math, and that's where Doc takes over, and if I leave you in base 2, you'll never make the connection. I've got to leave the base 2 soon and get into base 10. Oh, yeah, well, because this is easy to work with, and you made your own log table, and I went over to have the base 10 log tables duplicated, and the machine had a blockage of the colon at the splenic flexure, and we only got 19 copies out of it. Okay. There's always something to help. No, that's all right. That's all right, because now you have your answer. I suggested at Roanoke that when they got the new colonic machine that they call that room for identification the Reams room, because after you got finished. Well, all right. Now, all right. One more of the combination problem. We'll make this a doozy, and let's get to the answer as fast as possible. I hope I pick all base 2 numbers here. Continue multiplication here, please. Okay, here's the division. Those are all multiplied together. Here's the division. I will, as soon as I figure out what I'm going to write down. Okay. 64 times 32 times 2 times 16 times 8 divided by 4 times 2 times 64 times 8. Say that's easy. We got the answer. What answer did you get, man? 128. Does everybody agree that's 128? Let the teacher check. Okay, I'm going to make the problem a little simpler here because there are some things that are not necessary in this problem. Doing this problem by logs and throwing out the unnecessary things, which was to scratch off a 64 in the top with a 64 in the bottom and a 32 up there with a combination of 4 and 8 down here, which was the same thing, and a 2 in the numerator with a 2 in the denominator. The problem boiled down to simply the multiplication of 16 times 8, which is 4, plus 3, which is 7, and 2 to the 7th power is 128. Okay, this is what Doc is talking about thinking, because where did you learn to do what I just did now to shorten that problem? In the 4th grade. Okay, and so when Doc tells us, but you had that in class 1, you did. But you have to search it out, or go over some tapes from previous classes or something like that to find it. It'll be there. Nobody said it would be, easy. Okay, let's proceed to powers and roots. And I think this was good to do it on base 2 because we'll be able to make the transition to base 10 here then rather rapidly. And you don't have all the base 10 tables. I'll have to give them to you so you can fill in a table. All right. We're going to raise numbers to powers now. For example, take 16 and square it, which means what? 2 factors of 16. Okay, that'd be 16 times 16. So Doc says 256. That's right. He's got the thing memorized. Now, how do you do that when you're raising to a power? Okay, since it really boils down to 16 times 16, it was a multiplication, right? So it was 4 plus 4 is 8, and 2 raised to the 8th power, 256. Let's change this number now. Instead of to the 2nd, let's take it to the 5th. Now, without writing down anything, what does that problem boil down to? It boils down to 16 times 16 times 16 times 16 times 16. I don't want to make this tedious, but I really want to drill it home. That means the 16th have a log of how much? 4. So it became 4 plus 4 plus 4 plus 4 plus 4. How many times did I say 4? I said it the same number of times as the power I've got up there. So instead of painfully saying 4 plus 4 plus 4, I could really make it shorter by saying 5 times 4. Okay? That gave 20. What is that 20? It's the log of the number 16 raised to the 5th power, and you don't have it in your table. But you have enough there to figure it out. Isn't 2 raised to the 20th power the same thing as 2 to the 10th times 2 to the 10th? Sure is. And what's 2 to the 10th? It's 1,024. So the problem really became, now here you would have to do a little bit of work. You'd have to take your computer or something and multiply 1,024 times 1,024 to get the answer, or you'd have to build a bigger log table. That's all. All right, so you found out that raising a number to a power means to simply, here's our base of 2, and we have many numbers in the n column which are built on that 2, and one of those numbers is 32, for example. If you wanted to raise 32 to the 3rd power, what is the log of 32? 5. 3 times 5 is 15, and look in your table for 15. You don't have it there, but a few more lines down you would, and look up the anti-log and you'd have the answer. Okay, 32,768, he says. As long as he said that, we'll make it right for the tape. 32,768. Okay. Now, if raising a number to a power is the same thing as multiplying the power times the log of that number, guess what taking a root is? If we wanted the square root of 1,024, what's the answer so we can get to that quickly and then we'll figure out? You guys that know how to work them. 32. All right. Now, how did they get it so quickly? They took the log of 1,024, which is 10, and you cut it in half, or in other words, you divide it by your root index, which would be in here. Square root, the index is 2. So the 10 divided by 2 is 5, and the 5 is the log of the answer, 32. See? All right. Let me give you one similar to that. Ooh, we ran out. Okay, that's fine. I don't like the paper anyway. Let's say we want the... Can't hear you. Oh, all right, fine. The square root of 1,024. And a little problem here. The square root of 1,024, we usually don't write the 2 in there. We assume, we know, we accept, all right? Because somebody's going to say something about assume. All right, we accept that there's a 2 in there, but I wrote it in this time. That's the root index. It becomes your divisor, right? The log of 1,024 is 10. Divide it by the root index, giving 5. The 5 is the log of your answer. Find the anti-log of 5, and it's 32. The square root of 1,024 is 32. Sandy? All right. the number we're looking for, n, is equal to the square root of 1024. Okay, the square root can be written in this fashion also. Okay, just the plain square root. If okay, for the benefit of the tape, it's written as 1 over 2. That's the square root. Then how would you write the cube root? 1 over 3. The fifth root, 1 over 5. All right, I want the fifth root. Well, we'll start with the square root. We want the square root of 1024. All right, I didn't want to get this far into the writing of logarithmic equations, but maybe it'll help. The log of the number that we're looking for is equal to 1/2 of the log of 1024. Does that help? It puts it all together in one statement. The log of the number we're looking for, and what number are we looking for? The square root of 1024. The log of n is equal to 1/2 of the log of 1024. Next step. The log of n is equal to 1/2 of, now from your table, what's the log of 1024? It's 10. All right, so the log of n then must be, what? 5. Look in your table then and find 5. So if the log of n is 5, then n, the number you're looking for, is the 32. Is that clear? Okay. Are you able to do some log problems today you weren't able to do yesterday? Of course you are. All right, but it's painfully slow, I know that. But we have already covered about 3 classes in advanced algebra at the high school level. Okay? So you shouldn't be scared about advanced education for those that never had math at that level, because you see, it's easy. It's a powerful tool is what it is. Can I have a little work in base 10? Totally. Now, he'll knock the 0 off and work in what he calls base 1. But what I'm saying is, in going out to base 10, it'll be a much smaller step to make than it was where we were yesterday. Now, here's the key thing to this whole thing. What we've been presenting here is the very first grade, lowest level type of logarithms that we can work with. This is the infant stage of logarithms and what can be done with them. But what you have to do now when you get home, I'm going to introduce the base 10 now, and what you're going to have to do is practice with what we have had time to give you here, and find someone at home, like a senior student at the high school level that's been a math major. You know, give them $5 an hour, looking for moonlighting, and give them $10 an hour, and have them sit down with you and just grind through those logarithms until you have it. You'll have to get a tutor to really master the subject.
Back in the Depression, they charged me on some of this $50 an hour, equal to about $5,000 an hour today.
Yes, sir. It depends on the individual whether he can take a book and teach himself. It's self-starter, self-discipline, and it takes a tremendous amount from an individual to take a book and glean from it everything that we need. So, I'm going to do this. I'm going to take all of the information I'm presenting here, as much as I think is useful in making the transfer to the relative math, and duplicate it. I will turn over whatever work that I put in that with the tables and give it to Doc or Fern or someone, and if they want to disseminate that and mail it out to you in a couple of weeks' time so that you can spend the next month or so working on that, and I will put example problems in related to what we're doing here today, and you have to get into it then and do it. I'd be willing to write that all up, and I'm sure that Doc will mail it out to you. All right. Now, I did try to get tables for you to work with. I told you the machine broke down. So I'm going to have to give you a few of these numbers. We don't have time to duplicate the table by dictation, so I'm just going to be able to take a few and tell you where those numbers came from, and we're making a big jump now at this point. Someone did ask me to define powers and roots again, so I'll do it very quickly. Take the number 100. I'm leaving base 2 at this point. Just take the number 100. And I'm looking for a root. Now, a root is a number which can be, I'm going to use bad mathematics language here, but it's easier to understand. The root is a number multiplied by itself that would give you 100. That's the square root. Okay? So the square root of 100 then is 10. Okay? And this is the way it would be written in exponential language, 100 to the 1/2 power. And you know that 1/2 is a logarithm. Okay? So that's 10. Again, 10 is the square root of 100. Now that defines root for you well enough that you could tell me what is the square root of 64. 8. All right? Take the number 5 and raise it to a power. Raise 5 to the second power, and you'd have what? 25. We're just going in the other direction. It's like putting it in reverse and going backwards, and putting it as 5 to the second power is like putting it in forward gear and going forward, if you want to look at the analogy. So then 5 to the third power would be 125. Okay, is that a correlation made between what we're talking about with root and power? All right. Now we do have to proceed. I will have to start going rather rapidly, and you're just going to have to hang on and wait for the brochure to come to you. You can pick up a math book in a bookstore, but I am not going to put all of the things in this brochure that lead up to it, because the theory would overwhelm you, and it's not necessary to know it. Okay? You mean on the numbers here you're talking on the table? Yes, that's true too. But you can get a log table in the back of any good math book, all right? Yes. Okay, thank you, Doctor. Here we go. Now graduate from base 2 to base 10. All right, 10 to the first power is 10. The first entry that you'll have in the logarithm table that you will see in the back of the book is a 1 0 here. You can't look at that number as 10. It's a number sequence. It's 1 0. It's either 1 or it's 10 or it's 100 or it's a billion. It doesn't make any difference, and we're getting a little closer now to big numbers and how to handle them with little small shorthand, okay, symbols. Now we know that 10 raised to the first power is 10. All right, in your log table they will not write down the 1, okay? What they're going to write down here is 0, 0, 0, 0. Why? Because I just want to proceed forward here to look at 10 to the first power is equal to 10, and 10 to the second power is equal to 100, and 10 cubed is equal to 1,000. There are many numbers between 10 and 100. Therefore, if we can express these numbers on the right-hand side, which are the numbers in your table under the letter n, in the exponential form that I've written here, then what would I have to write here in the left-hand side in the exponential form, for example, to represent 50? Do not say 10 to the 1.5, because that is wrong. This is not a straight line function, it's a curved function. Okay? And you can see that readily from looking at the next entry. If 10 squared is 100 and 10 cubed, and that's only one step in the exponent, gives us 900 steps over here, whereas one step between 10 to the first and the 10 second gave us 90 steps. Then something is changing rather rapidly in those numbers in the exponent, which is the logarithm. Do you see that? The results of a small change in the logarithm causes huge changes to occur over here at an ever-increasing rate, which in engineering or physics would be called acceleration. Okay? Now, the table, again, in your book, where it will have the 4 zeros, here's what they're putting in. 10 to the 1.0000 power. That's another way of writing 1. You can see it. This is the portion they're putting in the table, the 4 zeros. And the next entry in the table is going to be 0043. And this is what it means. 10 to the 1.0043 is equal to something more than 10 but less than 100. Do you agree? Okay, and the number is 101. Sorry, correction on that. On your tape, go back and put a decimal point in. 10 to the 1.0043 is equal to 10.1. I said it was between 10 and 100, and then turn around and say 100. I'll tell you why it's difficult to teach. Because you're holding a microphone, trying to keep it out of your mouth, say the right words, think and write at the same time. And that is not all that easy to do and get everything to come out right. You've heard people say many times one thing, and they look at you and they say, but I told you it was 5, and they wrote down 3 or something. It's very easy to do because we're doing too many things at once here. All right, the next entry in the table would be 0086. What does that mean? It means the number 10, which is the base, is going to be raised to the 1.0086 power. All right, now, thinking time. What number corresponds to 10 to the 1.0086 power? Right. Now that is a huge jump you've just made in seeing that it was 10.2 because we're on base 10. These things are proceeding by tenths now. Okay? I will as soon as I can get, because I haven't built a table here yet. The next number would be 0128 in the table. Now here's the way you see them in the table. The heading of this column here is 0. So it's 10.0, and then the 4 zeros are under it. And you understand what that means now. The next column will have a 1 over it, and the number is 0043. The next column to the right would have a 2 after it, and that is 0086. And I'm not dictating any more of the table, but that's how it's built, and you'll know how to read it when you get to it. Okay? Okay. All right. We'll spend just a little time in that transition because it's getting from small numbers to big numbers. Yes. 0086. If you can write rapidly. The next one, which would be under the 3, is 0128. And if you're writing on your notebook paper, 0170, 0212, 0253. 7 corresponds to 0294. 8 corresponds to 0334. 9 corresponds to 0374. Now, in the low part of the table, in these numbers, the jumps between those mantisses are running about 40 steps, aren't they? All right, I want to just take at the end of the table. Yes, they go across, just I started here. 2, 3, 4, 5, 6. Okay, that's how you'll see the table. Down at the bottom of the table, they have the number sequence 99, and under the column headed 0, the mantissa in there is 9956. The next number to the right, which would be your number 1 column, no, this same table, ma'am, it's way down. See, it starts at 10, and I'm clear down. I've jumped all the numbers. I'm down to 99. It's 9956. Yes. On this column, it would look like 10, 11, 12, 13, but it isn't, right? It looks like it, but it isn't, because that might be 100,000, and the next number might be 100,000 or 110,000. You see how you have to look at it. And the difference is going to be in the whole number portion of the logarithm. I'll get to that in just a moment, and then I can wrap this whole thing up. All right, so the number sequence, again, 990 is 9956. And for the 1 column, I'll give you one more here, it's 9961. Now, I teach it completely different than the math books do. I call steps in between. Up here, the steps were 43 between your first 2 entries. How many steps we've got down here? 5. You see what's happening all through the table. It starts out in the numbers that are close to the 1-0 sequence as being big jumps, and the numbers at the higher sequences have littler jumps. And if you drew a curve of this thing, it would look like big differences here for a little bit of distance going to the right. There's big differences, and then the differences aren't so big anymore, and it starts flattening out, flattening out, flattening out, and that is called a log curve. And bacteria growth, if I remember correctly from microbiology class, the bacteria grow on a logarithmic curve basis. Isn't that true? That's correct. You fellows that are in the laboratory all the time can explain that to your mates out there. Okay. Now, we don't have time to duplicate the table, obviously. You know how the table is built. I just want to say this. If you would look in the end column and wanted the log now of the number 563, this is what you would do. You'd look under N for the sequence 5, 6, then go across your columns until you got to 3, okay? Now, and the 5, 6 line, go to the right, come down like this, and where it meets will give you the decimal portion of the log, the part after the decimal point. This whole table is the part after the decimal point. So, since you responded well to the log equation before, the log of 563 is equal to the first thing you have to supply, which is the power on 10. And we find this number. Now, where do we find 563? We find it between 100 and between 1,000. And what's the log of 100? 2. The log of 1,000? 3. So we know that the log of 563 has got to be between 2 and 3. So it's 2 point, and you look in your log table, and you draw out the decimal portion, which is 7582. Okay, all right, just very quickly. 10 to the first power is 10. 10 to the second power is 100. 10 cubed is 1,000, and many numbers in between there which are not expressed. But if you express them as a 10 to the something power, the something would have to be, if the number were in here between 10 and 100, it would have to be 1 point and then a decimal portion. Is that clear? And if you had a number that was located between 100 and 1,000, like we've got here, 563, then you know the log of that number has got to be between the 2 and the 3. And where is it in between? The table tells you. It does a lot of complicated mathematics and presents it. There's a lot of calculus in there to build that table. Okay? So they just give it to you. The fractional part of the logarithm is in the table. Okay, yes. That's correct. This table is all in the base 10, right. If they say common logarithms, they're talking about base 10. Now, how far? There really isn't much in there. At this point, I must say to you that you have to go home now, get a log table, look at it, find somebody that knows how to work these problems, and jump into them with both feet. Can I rush you that much? And all right. Now, what is the purpose of this log table? The purpose is that we can handle very large numbers with a very easy way. I said that you could look at that number sequence, 563, for example, with its logarithm being equal to 2 point something. But what if we looked at this number as 563,000 or 563 billion? We still can work calculations with those huge numbers easily. And I will propose just to run through an example here rapidly based on what you know in log 2. I'm going to do a multiplication problem of two very large numbers, which would be equivalent to figuring some energy in something, somewhere, and do it an easy way. Okay, we're going to multiply 500, well, we'll say 5,630 times 5,820. All right, now that would be a fairly large number of some kind, and this can be done easily with logarithms simply by looking in the table and getting the log of these numbers. The log of 5,630 has got to be between what and what? What are the limits? No, come on. No. See, 10 to the third power is 1,000, so it's got to be more than what? It's got to be more than 3. It's got to be more than 3. The log, I'll put a capital up there, is 3.7505. 7505. Okay, the log of 5,820, number of feet in a mile, is 3.7649. Now, would you rather add those two numbers or sit down and multiply those out? The answer is obvious. You'd rather add those two numbers. Was there a question there somewhere? Or, I thought I had a comment. All right, let's add them. 5 and 9, 14, 5, 11, 14, 15, 7. Okay, the sum of those logs is 7.5154. Agreed. All right, students, now tell me, what do you do with the 7.5154? One volunteer to tell the class what to do with it, sir. Perfect. Don't say any more. Find the anti-log. Now, how do you find that? Now, here's the one last step that I have to give you in using the table. In the table, will you find the 7? in the 0.5154. You will not find the 7, but you will find the 5154. So I search through the table here. It just takes a moment, and I get something close. I'm not even going to worry about getting accurate because the numbers are so huge in the energy calculations, it doesn't make any difference. We throw out a lot of it. If you were doing, we'll say, a $30 billion deal on something, would you be concerned really about $100,000 one way or another, somebody scattered off with it? Of course not. Okay, 5154. All right, I happen to find the numbers. Now listen carefully, and for the tape. In the log table, I find the mantissa 5145, and right next door to it, I find 5159. It's in between there somewhere. I'm not even going to be concerned about it. I'll take either one of them. It doesn't make any difference. Now, I know that there is a technique the engineers out there are worrying. Tell them about interpolation. No, we're not going to tell them about interpolation. We're not even going to worry about it. Okay, I'm going to take the 5154, and the number sequence for 5154 is 32 in that left-hand column, and up at the top of the column above that is a 7. Does everybody understand where I got that? It came out of the... Okay, we have a big table here with N up here. Across this way, you got 0, 1, 2, 3, 4, and so on. 1, 4, 5, writing it on the page. All I did was zoomed across here, picked up the number with 7. So I've got a number sequence of 3, 2, 7. Can you hear? The only thing you have to do now... Can you imagine what it must have been like preaching to 5,000? The only thing you have to do now to get your answer is to work with that characteristic of 7 out there, and that 7 tells you where to put what? The decimal point. Okay, how many digits are we going to have before we write the decimal point in? 8 of them. There is one more digit. If you haven't seen that pattern yet, you haven't had your eyes open. There's one more digit in the whole number than there is the number of the characteristic. What was the log of 100? 2. How many digits in 100? 3 of them, 100. What was the log of 1,000? It's 3. How many digits in 1,000? 1000. Don't you see the little pattern there that you can use quickly? So all we need to get our answer here, and this is where I wind up, is 3, 2, 7. Now there are some other numbers in there, and with this thing here, out of space-age technology, a computer that has logs in it, all you have to do is punch a button and you got the answer. Okay? 327, and we would have some other digits here. If this log table were bigger, and instead of having 0043 as our first entry in there, it would have and now it wants to give up on me. Yeah, that's right, the space age. Yeah, you're right. It would get confusing. We'll drop it. Instead of looking for the other digits, we add them on. We got 1, 2, 3, 4, 5, 6, 7, 8, and the answer to that big multiplication problem is done very easily by adding those two together and just looking in the table, and we've got 32,700,000, and you can just, in the relative math, you drop all that. It doesn't mean a thing. Okay? In this one, the decimal was out there at the end, 32,700,000 decimal point. Okay, I'll write up this and some more things with more example problems on them, and it'll be up to Doc to take us from there and get us into the relative math, and I hope I haven't confused you too much. Okay, thank you.
Thank you. You did a beautiful job. You did a beautiful job. Thank you. Whenever you go to dealing with anionic and cationic energy that makes one cell, you run into big numbers very quickly. Very quickly. And unless you understand the theory of one cell and the theory of manufacturing and making one cell, you'll never understand the one atom, at least. I mean, not one cell, but one atom. And then the atoms that make one cell, you'll never understand the cause and effect of the gain and loss of energy. This is all disease is the loss of energy. Good health is prime energy. It is energy at its highest level. and I made the scale of 0 to 100. 4 is called the PNR line, the point of no return. After it drops to below 4, it's the point of no return, unless God does a miracle. It's considered raising the dead when you drop to 4. However, the person may be still talking and may be still conscious. I saw a patient in a hospital that was very jolly and didn't even look sick, and yet her energy was 3. And the cancer had entered the spine and was moving up the spine at the rate of 1 inch an hour. I didn't believe it when I ran the first test, so an hour later I did another test, and I found it moved up 1 inch. I went to her husband, who was the head technician in the hospital laboratory, and that was his wife. And I asked him, was his doctor on the floor, and he said yes. I said, in the hospital. That's what we say, is the doctor on the floor, means he's in the hospital. So he had him come down, and I said, doctor, it's too late. It's too late. Her energy level is 3, and she approximately has less than 40 hours to live. It's too late. Oh, no. He said, she'll be here for months yet. I said, no, doctor. And there was the poor man standing between 2 doctors arguing about how long his wife was going to live. And I said, there's nothing you can do now and nothing I can do. I said, the organs in the lower abdomen are already caving in. And I said, it's beyond what you can do and I can do. So I said to the man, I said, when your wife passes, please call me. So it was approximately 4 o'clock in the morning, about 19 hours from the time that I ran the test. He called me and he told me his wife had just passed. So what I'm trying to say is, this energy table, you better believe it. You better believe it. We've also can predict the time of death, sometime weeks in advance, months in advance, or even years in advance, that they do not change their habits and their plans. While I was in this hospital this last time, the doctor brought me, one of the doctors that taken the course brought me the numbers of a patient. And I said, doctor, it's too late. It's too late. He said, how long has she got? I said, 30 days. And she passed on the 29th day. Her energy was below 4. And whenever, in other words, I'll try at 4. But when it's below 4, I won't. Or if it's 20 and dropping so much every day and we can't stop it, there's nothing I know to do. I cannot keep you, or there's nothing I can help you with. So this is how I know, is because these numbers are too big, they're too far out, they're too great to try to even comprehend unless you put them in small numbers and forget about the zeros. And we'll learn more about that in the next course. I can readily understand, I mean, the ABCs of logarithm, why you don't understand the XYZ of it. I'm turning this over now to...
Now is the time to turn tape over.